So far, we have seen how to fit a simple linear regression, multilinear regression, and polynomial regression. Remember, fitting means to find the coefficients that minimize the loss function. Consequently, we have more than one model to choose from, and therefore we need a formal way to choose a model. We start, as in the KNN model, investigating the error for each model. So let's start with the training error. Now, just because we found a model that minimizes the square error, it doesn't mean that it's a good model. We can investigate the R-square, but also we should visualize and investigate the fitted model. The example on the left, we have a model fitted on the data, and the MSE is very high, but that is due to the noise in the data. We can only see this if we visualize the data and the model. On the right, we have 4 models, all with equal MSE, but for very different reasons. Now let's go to the test error. We know that we need to evaluate the fitted model on a new data that the model did not train on, what we call test data. The example on the left, we have test data to be on the lighter dots and train data to be on the darker dots. The training MSE here is 2.0, where the test MSE is 12.3. The reason for that is because the training data contains a strange point, an outlier, which confuses the model. Fitting to meaningless patterns in the training data is called overfitting. Finally, before we delve into model selection, it is worth interpreting the model. Here I have 2 models with sales and some budget. On the left, the MSE is low, but the slope is negative, 0.05. That means the larger the budget, the less the sales. On the right, again the MSE is low, but the intercept is negative, which means that for very small budget, we'll have negative sales. Both models do not make sense. Either the data are wrong or some assumptions we made are incorrect. For model selection, we want to emphasize to the generalization error. We know to evaluate the model on both train and test data because models that can do well on the training data may do poorly on a new data, which we call overfitting. The ability of the model to do well on new data is called generalization. The goal of model selection is to choose the model that generalizes the best. Model selection is the application of a principal method to determine the complexity of the model. For example, choosing a subset of predictors, choosing the degree of the polynomial model, etc. A strong motivation for performing model selection is to avoid overfitting, which we saw can happen when there are too many predictors, the feature space has high dimensionality, the polynomial degree is too high, and we consider too many cross terms. It can also happen when the coefficient values are extreme. We have not seen this yet, but we will in the next sections. How do we go about model selection? First, let's talk about the data we'll use. So far, we have been using train-test splits, which we did randomly. We use the train to fit the model, and we use the test to test the model performance. To do model selection, we introduce a different subset, which we call validation, and we use it to select the model. So now I have 3 subsets: train, validation, and test. We use the train to fit the model, we use the validation to select the model, and we use the test to report the model performance. Just remember never to use the test set for training or model selection. There are 4 ways of doing model selection. The first one is exhaustive search. The second one is using greedy algorithm. Third one is fine-tuning hyperparameters. And finally, regularization. Let's start with exhaustive search. An exhaustive search means to compare all possible models and pick the one with the best generalization error, or lowest error in the validation set. For example, how many different models do we consider when we have J predictors? Again, an example is 3 predictors. We're going to have a model with 0 predictors, only including the bias. It's going to be only one model. Models with 1 predictor, we have 3 models. only consider x1, only consider x2, or only consider x3. Models with two predictors will be x1 and x2 together, x2 and x3 together, and x3 and x1 together. Models with three predictors will be only one that includes all three predictors. How many models we have in total? Is 2 to the j models, which is prohibitively expensive, especially when j is large. For example, if j is 10, we have 2 to the 10, which is approximately 1,000. That means we have to fit 1,000 models and evaluate 1,000 models. Now let's move to greedy algorithms. Greedy algorithms are algorithms that follow a heuristic of finding the optimal choice at each stage. In many problems, a greedy strategy does not produce an optimal solution. But these greedy methods can yield solutions that approximate the optimal solution in a reasonable amount of time. Stepwise variable selection is one such greedy algorithm. It is iteratively building an optimal subset of predictors by optimizing a fixed model evaluation at each time. We start with the null model, the model with only the bias. For every predictor in the predictor set, we fit a model and select the model that gives us the lowest validation loss. We include the predictor that gave us the lowest MSE in the validation set to build models with two predictors, and we select the model with two predictors that give us the lowest validation loss. We continue doing this until we build a model with all the predictors. We finally select the model that gives us the lowest validation loss. How many models did we evaluate with this method? In the first step, we have j models. We compare a model for each predictor. In the second step, we have j minus 1 model because one predictor was already selected. For the next step, j minus 2 because the two predictors are already selected, etc. If we add all this together, we get order of j squared, which is much smaller than 2 to the j, especially for j large. Greedy strategy is much faster, but does not guarantee we will select the best model as with exhaustive search. Now let's move to hyperparameter fine-tuning. In this method, we turn model selection into choosing a hyperparameter. For example, polynomial regression requires choosing a degree. This can be thought as a model selection, and we select the model by tuning the hyperparameter, which is the degree of the polynomial. We have seen something like that earlier. We have shown fitting a model with 3 different degrees, degree 1, degree 2, degree 50. We said degree 1 is underfitting, we said degree 50 is overfitting, and we said somewhere in between is what we want. To formalize this, we span all polynomial degrees and record the validation and train loss. On the left, we have the lower degree polynomials, and we see that the train and validation loss are low, but can improve by increasing the degree. We call this underfitting. On the right, we see that the train loss continues to decrease. However, the validation loss increases. We call overfitting. We choose the degree that gives us the lowest validation loss.